cunning idea was to see how long it would take me to get from pH of very simple solutions, very simple acids, strong acids, to explaining buffer solutions. I was going to do a series of 2-3 minute videos, but I thought, oh hey, I like my Uzi classroom, so let's play with this. Okay, so the 2 little short introductory videos. If you've seen them, great. If you haven't, I'm just going to recap a couple of things. So I've got a strong acid. Right, the strong acid I've got, let's just dive straight into it, is going to be HCl, monoprotonic, protonoic, however you want to say it, 1 proton. And if you measure its pH, and let's say its pH is 1.15, 25, 35, well, 1.15. What's its concentration? What is the concentration? How many moles per dm cubed? What is the concentration of this thing? So how many moles have I got in a dm cubed in a litre? Okay, so it should be big H actually. I'm 2 things very terrible at spelling, and I kind of stick to the ideas. To recap, you can look at this as minus log to the base 10 of the concentration of hydrogen ions. I really don't. Now that you know, I understand what the definition of pH is mathematically. It's the log of the concentration, but it's the negative log. So what I do is I think, ooh, wow, if the pH is 1.15, actually the log of it is minus 1.15 equals the log of the concentration. So in terms of thinking, it's 10 to the power of minus 1.15. Yeah, and that's for the mathematicians. It's the power to which I've raised the number 10 to, and that will give me my concentration of hydrogen ions, and that's the way I'm looking at it. So I hope this makes sense. The 1.15 is actually, in terms of the calculation, minus 1.15, and you can see as I've written it, the flow from pH to 10 to the power of 1.15, minus 1.15. So now I need a calc. So what I'm going to do, I'm just going to go into, let's just go into, fingers, there we go, let me Google, and let's just put in, calc, let's see what calc brings up, because normally, whoops, I've made it disappear. Oh, that's what calculate or Google search. Google search. Let's see. Hey, log. Look at this log button here. We've got the INV, the inverse log. So let's try it. So how do I do this? Minus 1.15 inverse. There you see, 10 to the power x. Boom. Oh, I've got to do it first. Okay. Clear. So we press inverse, 10 to the power of x, and it is minus 1.15. It tells us that's a really interesting number. Oh well, 0.07. I'm going to leave it 0.07. Let's go 0.07 on. Let's go 0.07 on. Okay, so we have 0.071 moles per litre, moles per dm cubed. So that's just a quick recap of the calculation to do with pHs, and I've gone backwards. If this doesn't make sense, look at the 2 very, very short prerequisite videos to an introduction to this. Okay, so what we're going to do, I'm assuming, and I've made another assumption, that you've looked at equilibria. So I'm going to look at the ionic product of water and explain it, and some shortcuts. Let's just pull this sheet up here. So the ionic product of water means what happens when we talk about ionic product. What happens in water? I'm going to explain that first. So what happens? It's a little bit too fast for the computer. What happens in? That's disgusting. So let me move my tablet and select this selection tool. Let's select all this. Let's delete it. So what happens in water? Well, one idea that we should be starting to get into our heads is the fact that water is not just H2O, and it actually, the water molecules break down into hydrogen ions and hydroxide ions, and what we've got to kind of think about is, what is the concentration of these two? Well, they're equal. So in pure water, the concentration of H plus ions must be equal to the concentration of hydroxide ions. And we can write that as the ionic product of water, which we call Kc, right, is equal to H plus and OH minus. And this is from equilibrium over OH, that's H2O, the concentration of water. Okay. And we could have, if we look at this initial, let's write this out properly. If we look at this thing here, we look at it properly as opposed to just the explanation. What we've got here, you take water, and it spontaneously breaks down, but it's an equilibrium. Some molecules will break down to form hydrogen ions, H plus and OH minus ions, and sometimes OH minus hydroxide ion will react, will bond with the H plus to form water. So it's backwards and forwards. So here's an equilibrium explanation of it. Okay, so this is Kc. Well, Kw is, when we've got product, for those who are non-mathematicians, product means multiply. Right? So the ionic product of water is to take the ions of water and multiply them together. This is Kc, equilibrium. We can now call this Kw. What is it? The Kw, the ionic product, is the concentration of hydrogen ions, multiplied by the concentration of hydroxide ions, and that is it. Right, now, here are a couple of things that Miss Rickmald does. That's me. Am I ready for it yet? I don't. Why not? Why not? Let's have a look at what I think. What happens in my bizarre brain. Okay. What I think about is, I'm told constantly the pH of pure water at standard temperature and pressure, right? Standard temperature and pressure is 14. Sorry, 7. 14. I am going bonkers. Is 7. What's that actually mean to me? So when people say the pH of pure water, when chemists, and actually nowadays the general public say pH of 7, yeah. What does that actually mean? Well, what it means, if we remember, this is -7, and it would be 10 to the -7. This is a concentration of hydrogen ions, 10 to the -7. And if we look back at our original equation, we know that water breaks up into hydrogen ions and hydroxide ions, so they must be equal. So what I must have for Kw is, let's get this right now, is 10 to the -7. Here, I'm not going to write 1 times 10 to the -7, all like that is correct standard form. So if 10 to the -7 times 10 to the, let's put a dot in that, let's put times and times 10 to the -7. Okay, so what is 10 to the -7 times 10 to the -7? Oh, it's 10 to the -14. There we go, 10 to the -14. Now, listen, to go pKw and all that, but I'm not going to go into definitions right now. I'm just going to tell you about some ideas I have in my head. So what I know about the ionic product of water at standard temperature pressure, 25 degrees, is 14. So if I log it all, equals 7. Now, this is where it changes. When you multiply powers, you're actually adding them. Add 7. And so we're multiplying the indices, powers, call it what you want. And when you multiply powers, you actually add them. And this is what I think. So when someone turns around to me and they say to me, ooh, I've got a solution of pH. And if you see here, this is, let's change colour, this is where I've got pH. I know I'm rushing ahead a bit, and these ideas I want to come back to later. Where here, I've got a solution to pH 3. You can see my hydrogen ions here, and I've written hydrogen ion concentration in pure water is 10 to the minus 7. We could write that as a negative log of 7. This is the pH, and this is the actual concentration per moles per dm cubed. So it says, oh, do you know what, Mr. Iqbal? I've got pH of 3. What's the concentration? The pH of 3 is the pH. pH. What is the concentration of hydrogen ions? Well, that's 10 to the minus 3. 1 times 10 to the minus 3. It's never so easy. They always kind of add stuff to it to make it harder. As in, this is pH 2.78 or something silly. So what's the concentration of hydrogen ions? Well, 1 times 10 to the minus 3. That's easy enough. But what's the concentration of hydroxide ions? See, when I go and think about the ionic product of water is 14. They almost add, because it's powers to 14, so it means 3 plus 11. So when I have a pH of 3, the concentration of hydroxide ions, so this hydroxide ion OH minus, would actually, although it looks bigger, you've got to remember this is a negative log, so the concentration of hydroxide ions, let's write that here, I've moved, hydroxide ions is equal to 1 times 10 to the minus 11. And we would expect that. We expect some hydroxide ions. But when we have an acidic solution of pH 3, we would expect a silly low concentration of hydroxide ions. So that's my idea of KW. And there's many things you can do with KW. But I kind of was explaining KW and showed you some of my shortcuts. But maybe in this video we'll look at it in more context with exam questions. Okay, so let's play with something else. Yeah, let me show you how I work out the pH of a strong base. Okay, let's get rid of this. Okay, let's get rid of this. Close. Are you sure you want to delete whiteboard 2? Yeah. So now I'm going to show you how to work it out, the pH of a strong base. So I'm working out pH. A strong base will be something like sodium hydroxide. So let's have a look. Let's say we've got let's go for 0.1. 0.1. We've got 0.1 moles per dm cubed, moles per litre, call it moles per litre, moles per dm cubed, moles per dm cubed of sodium hydroxide. Right? So let's have a look. Let's think what this means. This, believe it or not, has nothing to do with pH. This is not an acid. This is sodium hydroxide. It's a base. So let's first work out, and the only thing I can work out is a concentration of OH minus ions. I cannot work out the concentration of hydrogen ions. As I said, it's a strong base. Let's work it out. So what's the concentration of OH minus ions? Well, that's easy. It will be moles per dm cubed. It's a strong base. All sodium hydroxide dissociates. So what's its pH? Well, first of all, we would do log 0.1. So this is the POH. So this is the concentration, and we'll write it here, the POH. It's like the OH, but it's the negative log of the concentration of hydroxide ions. So it's the same thing as pH, but you're using hydroxide ions. Minus log to the base 10, and in here we have 0.1. Okay? So what I'm going to do is use my cool calculator on Google. Let's just write that in there. I'm writing kind of slow, 0.1. Okay? So let's go back to Google. 0.1. Okay. I'm clear. So I want to log 0.1. This is minus 1. So log minus, and gives it minus. So I put log 0.1, that's -1. However, I want the negative of it. I want the opposite of it in terms of mathematics. So log to 0.1, which I put in the calculator, was -1. However, we do the opposite. We've got a negative sign here, so the POH is 1. Okay, so let's go back to KW and watch what I do. KW. I'm assuming, well, let's say it's at 24 degrees. So KW was the concentration. So I did PKW, but it doesn't matter. I'm going to put P here because I'm looking at logs, PKW, the logs, the negative logs of the concentration. So remember we said they must add together to give me 14. So I've got POH. So the pH is, I don't know, plus the POH, which is 1. And the ionic product of water is 14. 1 times 10 to the minus 4, so 14. So all I do is take 1 away from it. And if you think about it mathematically, it's quite easy. It must be 13 plus 1 to give you 14. So the pH is the pH. If you remember, we had pH. Now I'm going to start using, I have started using a bit technical jargon here. pH equals 13. Yeah, so pH down here, down this column, POH down this column here. So, where are we? Where's my cursor gone? Wait. The POH was here. This is POH. Right there. Okay. I hope that explains how I've used pH and POH to actually POH to work out pH, and all I've done is subtract it from 14, and that's it. Yeah. And just to go into a little bit more detail, I then know the concentration of hydrogen ions is 1 times 10. 1 times 10 to the minus 13, and you expect that very, very low concentrations of hydrogen ions. Okay, so we've had a look at pH, the ionic product of water, how I mess about with it in my head. So, we could do the opposite. If someone gave me a pH, I could work out the POH. Okay, something had a pH of 3. I know the POH will be 11. If it had a pH of 6, I know the POH will be 7. Right? Well, no, it wouldn't. It would be 8. 8 plus 6 is going to be 14. I could get the basic maths right. Okay. So, what I want to have a look at is, if I look at my nose, weak acids. Right? So, let's just delete this and let's have a look at some weak acids. Well, we've got 18 minutes. Come on. Close, yes. So let's have a look at some weak acids. Here we go. We'll do a little drop down arrows. I've never used that drop down arrow. Where's that drop down arrow? Tab options. Background color, rename, take a snapshot. Oh, rename. Let's call this one weak acids. Okay, so we'll have a look at weak acids here. That's cool, isn't it? Didn't know I could do that. Okay. The most common one you're going to look at is ethanoic. Ethanoic acid is CH3. Oops, that's a 3. COOH. This is ethanoic acid. Most common, sometimes they be propanoic, but it's really the same thing. Can I say that? Okay, fine. Plus H2O. Alright. And this will dissociate. It will not completely form the entire products. So, I'm going to add this in for just a bit detailed. The problem we have is, and one where they can confuse you slightly, is by giving you this. Well, the reason they give you this is we don't actually have free-flowing protons. we actually have the hydronium ion, which would look like this. So we've got COO minus, because it's lost a positive, and what would form is the hydronium ion, which is H3O plus, which is actually how the proton, this acid part is moving around. You don't have H plus flowing around all by its lonesome. But I don't like that, it's a bit complicated. So what I do is forget the H2O, forget the H2O from here. So what you're actually left with here is H plus. Let's just simplify this. Let's just delete the things that. So now that you understand why it is what it is. Oh, you still got that there. Let's get rid of that as well. We're just going to quite simply write what we're used to, which is H plus. That's a little explanation. Let's now rock and roll. Okay. From very what did we do? We did equilibrium. So I'm going to write Kc, because that's what equilibrium is. But instead of writing Kc, because it's specific for acid, I'm going to write Ka. And that's all. I've just renamed it specifically for acids as the acid dissociation constant. Okay, at the top we've got our products. I did it. I've got to write very neatly because I've got the most disgusting handwriting. CH3, COO minus. These are the products. This is what it dissociates into. And so you've got ethanoic ions. I've really struggled not to say chloride ions. And these are protons or hydrogen ions. Let's put a line under it. Let's see how neat I am. Hey, that's not bad. Underneath it we have the concentration. Right, CH3. COOH. Okay, so I'm going to make some assumptions here. Some quite sound assumptions. My first assumption is that these two, let's change colour, call them A and B. Black. I haven't used black for a long time. Here, A and B are two products. They're equal to each other. Well, of course they are, because, you know, one molecule of ethanoic acid dissociates, breakdowns into one molecule of ethanoic ions and one hydrogen ion. You know, you're going to split it, break it in two, you're going to get two pieces, and the number of pieces you're going to get is equal. You know, if you break 10 sticks in two, you're going to have 20 pieces. You know, if you break them different lengths, you're going to have the same number of. Anyway, you get my point. A and B are going to be equal. If you don't get my point, leave a comment. Okay. So let's have a nosy. I'm going to look at calculating pH of a weak acid. Let's have a look. Let's say we've got 0.1. Yeah, that looks good. 0.1 is a nice number. I couldn't keep up with my notes, but I've got so many notes. It's just so we've got 0.1 mole solution. Okay. So what we've got to know, they've got to give us, if they're asking a pH solution, they've got to give us Ka. They must give us Ka. Right? And they will give you, it will be 1.74 times 10 to the minus 5, and it will always be, in your exam, it will be that. So my Ka is 1.74 times 2, wait, whoa, I'm going all over to 4. I really need to learn how to write properly with these things. Times 10 to the minus 5. My handwriting's getting worse. Ugh. Maybe I'm not comfortable. Maybe I need to be less. Maybe I'm too comfortable. 10 to the minus 5. Yeah, too much software running. Maybe I need a bigger computer. Yeah. Okay. Now what I can say is, as much as A and B are equal, they're also really, really small. It's a weak acid, so A and B, hydrogen ions and ethanoic ions, are going to be really, really small, but they're going to be equal. So what I'm going to do is two assumptions. I'm going to assume, right, they're both the same number. When you times the same number together, you're actually squaring it. Let's put a positive charge in. Oh, my handwriting's getting near. So you're squaring, because it's going to be A times A, isn't it? Because A and B are the same, therefore A times A. So it's squaring over. And I'm assuming the assumption I was making is the amount of protons being formed, the amount of dissociation is so tiny that there's no point trying to deduct it from my concentration. So I don't know, 0.1. So what I'm going to say, what I'm actually saying is the number of ethanoic acid molecules that dissociate is so small that even when it reaches equilibrium, it hasn't changed. Okay, so what do we do? Well, after we got to this page, we put all the numbers in. It's really difficult. You move the 0.1, so depending on whether you've been taught this floating ping or however, if you move this 0.1 across, like this point is dividing over here. Okay, so from GCSE maths, you take the divide 0.1 across the other side, it becomes a times 0.1. For those people who have been taught differently, you're actually multiplying the whole thing, the whole equation by 1.7 by 0.1. So it gets really a denominator. If what I'm saying is not making sense, ignore it. So for those people who are doing either A-level maths or such. Okay, so what you do is over here you times by 0.1, right? Times by 0.1. And this will give us the concentration of hydrogen ions squared, right? Boom, 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 boom. Okay, so what do we do? 1.74 times 10 to the minus 5. Here. 1.74 express minus 5 times 0.1. Da-da! Oh dear, I'd really like that. I don't know how to do it on here. So 1.7, 1, 2, 3, 4, 5, 6. Well, I don't know if I did that. I expect it because it's 0.1 is 10 to the minus 1. And there you go. I'm being a bit dopey there. But 1.74 times 10 to the minus 6. Okay, so 1.74 times 10 to the minus 6 is the concentration of your hydrogen ion squared. Right? Let's try 1.74 times 10 to the minus 6. Okay, and again, this is H plus squared. And if you look up there, you'll see it, H plus squared. So we need to do the opposite square. We need to find out what we've squared to get 1.74 times 10 to the minus 6. So we need to square root it. That's a 6. The computer system's been very slow. Down to the minus 6, I suppose 6 there. Okay, so let's go back to our purple root answer. Oh yeah, yes. We've got 1.32 times 10 to the minus 3. So the concentration of hydrogen ions is 1.32 times 10 to the minus 3. This isn't our pH though. Right, this is the concentration of our hydrogen ions. Now a lot of students just stop. Right. Okay. Got the minus 3 here. Minus 3. There we go. Oops, this is a hydrogen ion concentration, so pH minus log to the base 10. What I'm going to do is I'm actually going to go through the next calculation quite quickly because my dogs are going a bit bonkers. You can probably hear in the background. Let's make sure nothing naughty is going on. So, if the following calculation doesn't make sense, leave a comment. Email me, that's even better. So what did we do with this? I want to log it. So log my answer equals -2. And now we're going to times it with -1. Let's just get rid of the sign. So my pH is 2.8. Let's go for 2.88. Nah, I could just do 2.9. My pH is 2.88. 2.88. See, it's not a very strong acid. 0.88. Whee! It's nearly 1,000 times weaker than if it would have been HCl. And you're going to have to ask yourself, how did he do that in his head? And think about it. Till next time, maybe we'll look at buffer solutions then, and actually get as far as buffer solutions. Bye.